developer, and I am here with ThoughtWorks for more than 8 years now. Yeah, that's about me. And we have Shivani and Shubham as our speakers today. So before handing over to them, I just have a few things to share. So if you have any queries in between, you can put them in chat. We will try to address those. And also we will be having some time at the end where you can ask your questions if you don't need to ask in between. Yeah. Thank you again for joining. Over to you, Shivani and Shubham.
All right. Shubham, you want to introduce yourself first?
Yes. Yeah. So thank you, Kavita, for giving us a start. Hello, people. I'm Shubham. I have been with ThoughtWorks for last 4 years. I have started my career here in ThoughtWorks only and continuing. I work as an app dev. Have been working on Scala and Java and Akka, as we'll be talking about some Akka things. Over to you, Shivani.
Hello, everyone. Thank you for joining our talk on Akka Streams. So my name is Shivani Thorat. I work as an application developer in ThoughtWorks. I joined ThoughtWorks 1 year back, and I have an experience of more than like 2.5 years. So when I was first working in my first project at ThoughtWorks, which was TMT, I got introduced to Akka Streams. And so me and Shubham are here to share our learnings with all of you. So this is going to be an introductory talk. We'll start from the Reactive Streams, like introduction to Reactive Streams. Then we'll see how that is implemented by Akka Streams. And then we'll talk a bit about Akka Streams terminologies. Right, so I'll start sharing my screen. Just a second. So I hope the screen is visible. Yeah, okay.
Yes.
Yeah. So let's look at the agenda for today. So firstly, we'll look at, we'll see what is Reactive Manifesto. Then comes asynchrony, what is asynchrony and its possible solutions. Then we'll talk briefly about the Reactive Streams API. And followed by that is the introduction to Akka Streams, how Reactive Streams API interface is implemented by Akka. Then comes a concept called stream materialization in Akka Streams. Then we'll talk about backpressure. And finally, we'll talk a bit about Project Alpaca, which is like a big deal in Akka Streams. All right. So let's get started. So firstly, before going into what is the Reactive Manifesto, let's try to break down the Reactive Streams part, right? So firstly, we'll talk about stream. What is stream? It is a flow of data, right? In programming, you can say stream is nothing but a flow of data. And this flow might be finite or it might be infinite, like non-terminating. Then comes the second part, which is what is reactive, right? So as you can see, there are some traits that are shown on the slide. So according to the Reactive Manifesto, any application or service that embraces the traits that are shown here, which is responsive, resilient, message-driven, and elastic, is said to be a reactive system. Okay. So let's go and see what these points are one by one. Okay, why is this not working? I'm sorry. Yeah, okay. First one is, as I said, responsive. So your application or service is said to be responsive when it is capable of giving some kind of response in a timely manner, right? And this responses should come not only in favorable conditions, but also under unfavorable conditions. And being responsive under unfavorable conditions gives rise to the second property, which is resiliency. All right. And we can achieve this resilience using the two things that are mentioned below. First one is replication. Second one is isolation and containment. So what is replication? You can take an example where you have a service and you're providing some service over the internet, and the workload, you are experiencing an increasing workload of requests. So you can have different components of the same instance running in parallel, and you can serve those requests in parallel, right? Replicate your workload across several instances. So one way you can achieve resiliency is using replication. Second one is isolation and containment. So basically, isolation and containment, we can talk in terms of decoupling. And this decoupling comes in terms of time as well as in terms of space. So we'll talk about decoupling in terms of time first. So you can consider that you have to carry out a specific task, right? Your service is carrying out, so there's service A, which is carrying out tasks like a PQRS. So since you want to isolate, like this task is very big and you want to isolate that into smaller chunks, you create smaller services, and those services communicate with one another so as to carry out the bigger task as whole, right? So isolation in terms of time is that for the services, the communication between these services to take place, not all of them have to be present at the same time. That means all the services are independent units of execution and their clocks need not be synced. Everybody is operating at their own execution cycles. So that is isolation in terms of time. And in terms of space is, decoupling in terms of time, and decoupling in terms of space means that the processes that are communicating with one another to carry out the task, right, they do not need to be in the same context or same machine. Okay, now let's look at the third one. It's not. No. Okay, the third one is scalable. So we talked about this when we were explaining resiliency itself, that your application should be able to scale up and scale down according to the workload that it experiences. And the fourth one is message driven. That is all the data, that is all the communication that is happening in your application between processes or between services needs to be in the form of messages. So this is what the reactive manifesto's 4 traits are for any system to be called reactive. Now looking at this 4 traits, we understand that for your system to be resilient, right, you have to distribute your problem, you have to distribute your task, and you have to have small services, like you have services carrying out specific tasks, and there need to be some communication in between them. So here is where comes the concept of asynchronous boundary. Now, what is an asynchronous boundary? It is nothing but a logical separation between modules, right? So this separation can be between processes, the separations can be between threads, machines, actors, etc. And our goal of asynchronous boundary is to pass data between across this logical separation, right? So we'll take an example where we can see what are the possible solutions to overcome this goal or to pass this goal. First, let's take an example of, so this is an example in which we have a process P1 and a process P2. Process P1 is reading some customer details data from the database, and it has to send that data to process P2, right? So what will be the possible solutions for this? Let's take a look at the first solution. First solution is having blocking calls. So here you can consider P1 as the publisher, that is reading data from the database, and it is sending data. It has to send data to P2, which is the subscriber. So one solution is that you can have a blocking queue, right? You can just push the publisher can just push the data to the blocking queue, and the subscriber reads the data from it. But here, as you probably might have guessed, there's a problem that once, if you have a slow subscriber, that your process P2 is very slow, then obviously it will read data slowly from the queue as compared to the rate at which publisher will put data in the queue. So at one point, your queue will be full, right? And since your queue is full, as you know how blocking queue works, your publisher will be blocked. It won't be able to react to any other requests if they are coming in, or any other cancel requests. It will just be blocked, not be able to do anything. So this is not a very good solution, because we do not want to block on our resources, since resources are very precious to us, right? So just let's scratch this solution, look at the next one. All right. So the next solution is the one in which we have a process P1, and it is just oblivious of the rate at which, if the process P2 is slower or it's faster, it is not concerned. It just sends the data as it comes, as data is available to the process P1, it just sends data to process P2. All right. So since P1 is not concerned about process P2, there's one thing that process P1 will never be blocked, right? So there's no blocking call happening at the sender. But at the receiver, there's another problem, right? So since we considered this state earlier, your process P2 can be slower, right? So it might be overwhelmed by data. So it has two solutions. First one, it has to keep some bounded buffer, right? So as you can see, I've shown a buffer at P2. So if it is not able to process data, it will just let some data be in the buffer. And once the buffer like fills, it has to drop the data, right? Or the second solution is in which it can have an unbounded buffer. But obviously that will lead to another problem, which is out of memory exception, right? So our process might go into out of memory exception. So here we can see that even even you have a bounded buffer, right? So the process P2 just needs to drop the new elements that are coming in. The data transfer mechanism is lossy, correct? So it's not a problem for the data transfer mechanism to be lossy, but that has to be a choice that we have to make. So if we say that I always want the latest data or I always want the oldest data, so it's okay for me to drop some data and just keep the newly coming in data. That is okay, but we have to specify that, right? The data transfer mechanism that we are showing here should itself be non-lossy, but it is not a case with this push mechanism that we are showing here. So let's scratch this solution also and move to the next part. Yeah, so the third possible solution is the reactive solution, right? Which states that our process P1 should be non-blocking every time. Process P2 should also be non-blocking, right? No blocking calls happening ever. And the data, whenever we are transferring any data, if process P2 is slower, no data should be dropped. And obviously we should have, if we are having a buffer in between these processes, that buffer should be a bounded buffer, right? So that we do not go into the pothole of out of memory exception. So how is this implemented? So as you can see, the trick here is that there is, along with the normal data flow channel that is going from process P1 to process P2, there's another channel, which is a demand channel that is introduced, which goes from process P2 to P1. Now, what is the demand channel? This demand channel actually carries a signal of how many elements process P2 is able to process or can process. Once P2 will send a demand on this channel, then and only then will process P1 start pushing data on your data channel, on this channel, right? So as you can see that unless and until P2 states like it wants, like demands something, unless and until that happens, P1 will not push any data on this channel. So if your process P2 is slower, it will demand less on your demand channel, like it will demand less frequently. And that is how P1 will send data less frequently on the data flow channel. So this is how your process P2 will actually be controlling the rate at which the data is flowing, right? So our problem of the slow subscriber is solved, and we have done that using a bounded buffer, right? Okay. And also the demand actually that is happening, it can be batched. So if say process P2 say it has now it is able to process like 100 elements. So you can just say, give me 100 elements, and process P1 will send those 100 elements as they are available to it. So it's not like just one by one, the demand is happening just for one element. The demand can be batched also. So this is the reactive way. And we can see how is this implemented, right? So you might ask a question like, if process P2 is demanding something from P1 and then and only then P1 is sending data to P2, how is this non-blocking, right? There must be some blocking call happening. So let's see where the magic happens, right? So this is the Reactor Stream protocol, right? This Reactor Stream specification is basically an extension to Reactor Manifesto, which basically specifies rules for streams that are carrying out data processing using a bounded buffer space, right? So as you can see here, there are 3 interfaces. One is publisher, subscriber, and subscription. So you can consider our process P1 to be the publisher, process P2 to be the subscriber, and subscription and processor, I'll explain them later. I have just given this methods just for you to see that all the data, all the return types of methods, right? They are void. So there is no blocking happening anywhere. We look at how these methods map to the solution that we saw earlier. We look at that, but just take a moment and just see that everything, every return type is void. There is no blocking happening. So you just call the method and you just forget. It's just fire and forget. All right. Now let's look at how this Reactive Streams API like ties with your third reactive solution. Okay, so you have a publisher and you have a subscriber. So if the subscriber wants to receive any data from the publisher, it has to call the subscribe method on the publisher. So here, that is what you see in the first step. The subscriber passes its instance and calls the subscribe method. Now, once publisher receives this subscribe call, it creates a subscription object and it passes it back to the subscriber using the onSubscribe method of the subscriber object it just received. Right. So now subscriber has the subscription method. Now, whenever subscriber is wants to is ready to process data, it will just say subscription.request. Now you can see here that as you can see here, subscription.request takes some like long element, right? So this is nothing but the number of elements it is able to process. Okay, it is able to process. So okay, yeah, so we request, and once we request those data element, then and only then the subscriber, the publisher will send the element back to your subscriber. So your request here is your substitute, like is what the demand channel is, right? So the demand channel that we saw earlier, that is nothing but your request on subscription object. So this is how it works. This is the underlying mechanism. So, but this API, as you can see, all the methods are abstract. This is not for us to use. This is for people who actually want to implement the Reactive Streams protocol, like what happens, what extra things happen on subscribe, what happens on error if there is some error while transferring the data. So all this specification on all this implementation is actually carried out by the people who want to implement this Reactive Stream protocol and to give us something that we can work with, right? Like the Akka Streams API. So Akka Streams is nothing but an implementation of the Reactive Streams interface, right? So we'll move further. Okay. Well, as I said already, let's now just get started with Akka Streams. Enough about Reactive Streams introduction. I hope that you might be able to link how the Reactive Streams interfaces interconnect with Akka Streams when we go further. But talking briefly about Akka Streams, as I said, it is a library to process and transfer a sequence of elements, and it is an implementation of the Akka of the Reactive Stream interface, right? And it was created by Lightbend, and it provides Scala and Java APIs. All right. Okay. So as we saw the Reactive Streams publisher subscriber, let's talk about those equivalents in Reactive Streams. So this is a source. This is equivalent to publisher in Reactive Streams. It emits elements. The source might be a finite source or it might be an infinite source. That is, it might terminate or not terminate. Then there's a sink, which is equivalent to subscriber, which actually consumes element. That's why you just see one arrow which is pointing into it. And this terminates when or stops when your source stops. Then you have a flow, which is equivalent to processor, or in the Reactive Streams, it transforms elements. So you have one arrow going inwards and one arrow going outwards. So these are the three components like source, sink, flow that are like core components which you can use to create your stream or graph in Akka Streams. So as you see in the diagram below, I have connected the source to a flow to a sink and you get a graph. All right. So enough with the technical theoretical things. Just let's see as one simple example. which just demonstrates all these components. All right. Okay. Yeah. So for now, just ignore this boilerplate code because Akka Streams and uses actors internally. This is something related to actor systems, and it might be a very huge diversion right now. So let's ignore the boilerplate. So we'll firstly see a simple graph, how to create a simple graph. So this here we have a simple source, which will do nothing, but it will just emit 1 to 10 elements, and it will stop. And you have a simple sink, which is equivalent to subscriber. So the sink, what does it do? For every element that comes into the sink, it calls this function, right? So it will just print those elements out to the screen or out to the console. And this is how you create a graph using DSL. So you have a source and you connect the source to the sink using the to method, right? So let's run this and see what happens. Yeah. So as I said, the source is emitting 10 elements, and those 10 elements are going to the sink, and sink is printing them out. So that's why you see 1 to 10 elements over here. Okay. Now let's introduce flow in between the source and sink. So here I'm having a simple flow, which is doing nothing but for every element that is coming into this flow, it is just squaring those elements and sending it outwards. So this is how you connect a source with a flow, and that flow to the sink using the via and the to method. So I'll do one thing. I'll just run this, and now we should get squares of all the numbers from 1 to 10. Yeah, so we have the squares of numbers from 1 to 10. So you can consider flow, it is used to transform elements that are coming into it, right? So next, I want to introduce you with a few ways with which you can create a source. First, we already saw that you can give a range to a source, and you can create a source from it. Then you can also create a source giving a list, right? And this one is where we are creating a source from future. So future in Scala is something that is computed asynchronously. So you can consider it similar to the completable future in Java or deferred in Kotlin, right? So this is the source that we are creating from a future. We can also have an infinite source, right? So this source will just keep on emitting this one element, and it won't stop. It will just keep on emitting it infinitely. And this is how you create a periodic source. So if you want some source which has to emit a certain element in specific intervals of time, then you can use the tick method for doing that. So these are some of the ways with which you can create sources. And this is, let's move on to sink then. The first method, first sink, is the most boring sink. It is just ignoring whatever elements are coming into it, right? So this sink can be used where most of your processing and is done in sources and your flows, and you just want the sink to complete your graph, right? Then the second sink we already saw, like for each element, it will just print that element out to the console. And the third one is using third sink is actually taking just the head. So whatever elements come into the sink, it will take the first element and it will just complete the stream, right? So then the next thing we have flows. So flow is nothing but as I said, processor. So first one is the map flow that we already saw. And the second one is like take. So for all the elements that are coming into the flow, this one will take the first 10 elements and it will complete the flow, right? And you get a graph when you connect these components using via and to methods. So as you can probably see that you might have noticed that wherever I wanted to run a graph, right, I was uncommenting out this run method. So this was like this first, and whenever I wanted to run it, I just uncommented it. So why did I do that? So if all the run methods are commented out, let's see what happens. Yeah. So nothing happens, right? You just see this simple stream examples print line statement, which we have put at the start. So no data is flowing. So why is that happening? So this is where we want to introduce you with another concept, which is called materializing. Let's go back to the slides. Yeah. So what is materializing in Akka? So as we saw earlier, when you connected source with a flow to a sink, you created a graph, but nothing no data was flowing through the graph unless and until you called the run method, right? So this is how Akka streams actually work. Everything is lazy unless and until a terminal action is called on it. So in our case, the terminal action is the run method. So when you call the run method, that is when the resource allocation will take place, right? So if you are reading something from the database, then the database connection will be initialized. Since Akka Streams uses actors internally, actors will be spawned up. That will happen only when you call the run method. Until that, you are just defining your pipeline, right? You're just defining what will be the structure of your pipeline. There is no data flowing through it. Everything is static. So when that is calling the run method on your graph, is when you run the graph, that is equal to materializing the graph. Now, when you call the run method, this run method returns the value. Okay, so let's see what this value is. Let's do this thing. Yeah. So as you see, it is returning some value. It is not used. Okay, so what is not used, you can just consider it like unit in Scala or void in Java. We are not concerned about this value. We have to do nothing with this value, right? So we know that what kind of data is flowing through our stream. We have just integers flowing through the stream, right? And this materialized value is not used. So this states that your materialized value can be anything, and it does not have to have any concern with the data that is flowing through the stream, right? You can have a simple integer as a materialized value. You can have an actor reference as a materialized value if you are integrating with your stream with actors, or if you want to implement a pub sub mechanism, then you can have a subscription as a materialized value, which you can use to cancel the subscription later. This is a bit difficult concept to grasp. So we'll move before moving on to the demo, we'll go back to the slide and we'll see one more concept. So looking at this diagram indicates, right, what are these triangles? Every component has a triangle on top of it. So what are that? So this diagram indicates that when your graph is run or materialized, every component will give you a materialized value. Source will give you one, flow will give you one, sink will give you one, but your graph as a whole will have just one materialized value, right? So what will that be? It will be from the source, or will it be from the flow, or will it be from the sink? That we have to decide. Okay. So let's take one example in which we choose the materialized value, right? So that way you will get more grasp about what is materialized value actually, right? Okay. So as I said earlier, ignore this boilerplate. We'll take the similar example that we took in the simple examples, but now we'll have one added thing, which is a materialized value. There is a simple source, which is, as I said earlier, emitting elements from 1 to 10. But now, if you see this type of this type, so you can see this is a type of source, which is emitting out integer elements, and it is having some value. Now, what is this some value? It is the value that will be materialized by the source when it is run in with the graph, right? So just consider it to be some value for now. I have added a type alias for it to be understood better. Then you have a flow. This flow is also doing nothing. Whatever elements are coming into this flow, it will just print those elements and increment it and send it outwards, right? So if you look at this type, it takes integer elements, it gives out integer elements, and it also gives out some materialized value, which is also of times some value. Then you have a simple sink. This sink is doing nothing as before, just prints elements out to the console. If we look at the type sink, the sink takes in integer elements and produces this materialized value. Now, future of done, what does that specify? So when sync is done with processing all the elements, right, it will this materialized value, future of done, will complete, and then we can get that, yeah, my data has flown from my source, it has gone through the simple flow, and it has gone to the sync, and everything is completed. So let's connect these three things and see what we are getting, right? This is graph. I've connected it using the same via and two methods that we saw in the simple example. Now, if we see the materialized value, it is some value, but I don't want this value, right? I want the value from the sync. So how do we do that? Let's uncomment this out. Sorry. Yeah. Okay. So now, instead of connecting the source flow and sync with the via and two method, I'm using via materialized and via and two mat method. So simple source connects to simple flow via using the via mat, and then you pass a lambda to it, which says that take sources materialized value, and from the flows materialized value, take one value forward. Now I'm not concerned with both of them because I want the sinks materialized value. So I'm just carrying forward the flows materialized value. And then when you connect that to the sink, what you again pass one more lambda, which says that whatever materialized value you got from upstream, take that, take the sinks materialized value. And now we want the sinks materialized value, right? Future of done. So that's where I selected the sinks materialized value. And then you call the run method on that. So that is how you get a specific materialized value from the graph. So since this lambdas are very much common in Akka Streams, you have a syntactic sugar for it, right? So yeah. So if you see, I've used the same via mat method, but instead of lambda, I am doing a keep right, which is saying that from this both materialized value, keep the rights, that is simple flows materialized value. And similarly with the sync, from the whatever materialized value you get from the upstream, keep the right one, which is the simple sinks one. So I'll just do this, and let's see the type of the annotation. It is future of done. All right. I'll just comment this, and let's take one exercise. All right. We'll implement it together. So let's, okay. So what is the problem statement? This is just to explain you materialized value in more brief. So what we have to do is we have to get the total number of words that are emitted by the stream. So you'll have a stream which will give you out sentences, and you just have to calculate what is the count of words in all the sentences that are coming into the stream, right? So firstly, what we'll do is we'll create a source. We need a source that of sentence that will emit out sentences. Second, we need to count words in each sentence, right? And third, we need to add all the counts. So how to do that? First, we'll go with the first step, create a source of create the source. It is very simple. Since it is a list, you can create a source by passing the list directly. This is a sentence source. Second step is to count the number of words. So I can use a flow here. So whatever string comes into this flow, what I'll do is I'll just split it on the space character, and I'll just calculate the length. So my flow will take in a sentence, but it will give out a number that will be the number of words in that sentence, right? And now my sync. Now my sync, it will receive all the words, all the counts of the sentences. It just has to add them together, right? So we have this sync, which is performing a reduce operation of all the words that of all the counts that are coming into it. Now we just I'll just take it down. We just connect it using the via method and the to mat method. Since we want the count, right? We want a total count. That total count is actually the value that is materialized by your sync, and we want that. So I just connect sentence source and this flow using the via method because I'm not concerned whichever materialized value it takes. But when connecting it to the sink, I use a toMat method and I say keep right so that I get the materialized value of our sink. Okay, so let's run this. Yeah, it will run. Okay, let's see what happens. Okay, I guess this is running something else too. Yeah, this graph is also being run. Yeah, so we have a total word count. Like we were when we ran this graph, we got this materialized value, which is a future of integer. We are just waiting for that future to complete. We are calling the onComplete method. So once this future has some integer to emit, it will complete with success. So that's when we print out the value, right? Total word count is something. So we got 12 back. All right. So this is like very simple explanation of materialize. What is materialization in Akka Streams? This was a very this was very difficult concept that I found to grasp my head around, and we have tried to present it as making it as simple as possible, right? Okay, moving forward, you have to understand that graphs can be materialized many times, right? You can just create materialize many times is that you can run a same graph multiple times. So and every time it is run, the materialized value that will be created is different, right? So you can just create your graph, and you can, if you want to use it somewhere else, you can create it at one place and send it to other place, and then you can run it there. So every time it will produce a different materialized value. So that is one important point to remember about running the graphs, that is materializing the graphs. All right, we're all done with materializing. We will be moving to back pressure now. So what is like back pressure and how that back pressure like integrates with the asynchronous boundary thing that we talked in the first part. Let's look at that. So Shubham will be sharing the screen now and talking about it. Shubham, are you okay?
Yep.
I'll stop sharing.
Please let me share. So maybe I can start with addressing the question which we have in chat, and then take over for the back pressure. Just give me a second so I do all the things. Oh, not share, present one. Present. Right. So we had a question from Avinash asking, is it a replacement for Kafka or Akka things? Sorry, Kafka or RabbitMQ? The straight answer is no. But this is something which will help you deal with or talk to Kafka or RabbitMQ in a synchronous manner, where you have your data or your events in the Kafka or the RabbitMQ. It's a queuing mechanism, right? And in Akka Streams, you can treat Kafka either as a source where you are reading data from, or you can treat it as a sink where you are dumping your data to. So that's where the Akka Streams fit in, where you can write your pipelines of the data transformation, or you can write your clients to read the data from Kafka, or write it to Kafka. And yeah, so it fits into the graph. So the part of the graph which you're saying, right, it can be, we have a source and sink. Those are the places where Kafka and RabbitMQ sits, and the other transformation part can be taken care by the Akka Stream. So I hope that answers.
Yeah. Yes. That answers.
Okay. So moving on to back pressure. So we started with this only, right? We started with reactive streams, and that's where we were talking about we have a stream of data. We need to modify the data, transfer the data, do all the operations, but in a way where our sink is not overwhelmed with data, or we are not losing the data anyhow. So that's where the important thing of the Akka Streams plays, and maybe that's where we'll dive into. But before that, let's go to one more concept. I think most of the time we'll be talking code here. So, and I hope these Scala examples are simple enough for you to understand. That's something we forgot to call out. Yeah. So all the examples here are in Scala. Right. So yeah, before going to back pressure, let's try to understand this. So I have created a simple graph here. So I have a fast source, a simple flow which does nothing but just prints the element to console, and then we have a slow sync. A very crude way to create a slow sync. We are just blocking the thread here, but it's good enough for the example. That's why we are keeping it simple, right? So we have a slow sync here, which sorry.
इसे देगा कोई तो काम तो करबे करेगा.
There's some. Can you go on mute if you are not asking a question or saying something, please? Yeah. Right. So I have created a simple flow here, and let's try to run it to understand how this the data is flowing actually. So whatever we saw till now looked like a collection kind of thing, right? We have a collection of 1 to 10 elements, and we are trying to do some processing there. But maybe this is where we can see some differences and what Akka Stream really is. So we see, right, the first element goes through the simple flow, which just prints it out, and then we get for the first element, we get a print of the sync. Our flow goes till 100. If doesn't matter though. Then we have a second element which goes to the flow, then to the sync, then third element to the flow, to the sync, and that's how the data is flowing into the system. So one element is completing one stage at a time. It reaches to the end and then comes back to the source to read the next element, and that's how our execution is going on. And this thing in Akka Streams is called as operator fusion. So for example, we have a simple source, flow, and sync, and all the things are fused to each other. They are connected to each other, and they're working as if it's a single system, and the data is being processed. Whenever we complete one element, we go for the other element. But then we can guess, right? There is some synchrony here, that's how the data is being processed. And we don't want our systems to be like this. Though it works in a non-blocking fashion, though there is synchrony, and we want to scale up because we have multiple CPUs and multiple machines and whatnot. So that's where the async operator comes in. So for example, we have a source, and we have a simple flow, and we have a 4-core machine. We want to exercise all the 4 cores of the machine. Here, actually, I'm taking example of the thread, but Akka Streams uses something called actors. That's a whole different topic. But for understanding sake, let's understand it as threads. So we introduce an operation called async. What it will do is it will separate the execution of the two. We have a source executing in a different thread, and then we have a flow which will execute into a different thread. And what ties them in between, ties them together, is a bounded buffer of 16 by default, 16 size, which is introduced by Akka. And same thing happens here. There is a buffer of 16 which ties between this flow and sync, and both of them execute asynchronously. And just to demo that, let me just run it once. Yeah, just give it a second to run. And here we have, as I said, right, we have a slow sync. So here you see the first 16 element just came here instantaneously, and our flow printed them right away. But our slow sync is taking some time to process the element. So data processing is going on slowly, one by one element per second, but still we are getting all the elements which are being processed. So our simple flow has reached to 32. Slow sync is still on 16 to 23, but it's scooping up. It's trying to catch up with the thing. How is that happening? So as I said, right, we have a buffer of 16 introduced here, which will keep the elements. We have a buffer of 16 elements here, which will again. So when we start executing the slow, how the data flow starts is the sync will indicate demand that I'm ready to take the elements. That's how flow gets to know that the downstream is able to take the elements. Let's tell to the upstream that downstream is ready. So it will tell the source that I'm ready to take the elements, send me the elements, and then source will start emitting the data, whatever it is. In our terms, it's numbers. Simple flow takes those numbers, do whatever transformation it has to, and will put down into the buffer. Why in the buffer? Because our slow sync will pick up from there, and our slow sync is picking it up slow, right? So that's why this part of the stream processes elements very fast, the first 16 elements, but then slow sync is not able to take elements from the buffer. And that's where there is no more demand onto the simple flow because the elements are not consumed. So simple flow will say that I'm not able to process any elements. I'll tell this to, I'll not ask any element from the source, and then source is not asked for any more elements. So it will stop creating, producing more data or reading more data from whatever source it is. And that's how the back pressure plays out, because we don't have any more data flowing into the system now, because our sync is slow. And that's what is called as back pressure. So we are not really saying we'll not take any data, but in other words, we say that I'll not ask for any data so that the no data is read, and that's how we back pressure the data towards the upstream. And eventually, when we are at the source, no data is being produced, and that's how the back pressure plays. I hope it made few things clear about the back pressure, right? So that is how the back pressure plays in. But we, again, as Shivani mentioned when we were talking about the reactive streams initially, right, in the approaches, we still have use cases where we want to have buffers, or we want to have elements which are latest. We don't always want to wait for all the data. Say for example, if you have a IoT system and you are okay with dropping the data and getting the latest values of a sensor data. For example, you are reading heat, so you have a heat sensor and it's sending data. You are okay if a few values are missed, and if you are transforming them slow, but you just want to get the latest value. And for those use cases, we still have buffers, and we have the ability to drop the elements. So whenever we say buffer, then in Akka Streams, we'll need to tell two things: size of the buffer, because we are always bounded. We want to be bounded. And the other thing we want to mention is what happens if the buffer overflows. So here I'm saying drop the head. That is like drop the oldest element which we have in the stream. That's how it will play out. And for reference, if I just run this one, this flow also, right? We have the same structure. We have the fast source, a sync method in there. We are introducing the flow, one extra buffer here, and we have the slow sync. And let's see how does it execute the data, execute the things. Okay. Yes. So we see here, right, in the first go, all the 100 elements were computed. Can we guess why? If someone is interested. Okay.
Buffer overflows.
Yes, so the buffer overflows and we keep on dropping the elements, and we never say to the fast source from this stage that I'm not ready to take elements, because we are dropping elements on one side and we are asking elements on the other side, and that's how all the elements come into the memory. And the slow sync is taking elements at its own speed. So here we see, right, it is processing the first 16 elements, because those were the ones which reached the buffer initially, and the other elements were dropped. And after 16 we see 91, 92, 93, because all the other latest elements were dropped, and what we were left with was the 10 elements which were stored in this buffer which we introduced. And that's why we directly see 91, 90, 92 till 100. And that's how the buffers play up. But as Shivani had said, right, here user or we as a developers are the one making the choice that we want to drop the things if we get extra. And by definition, the mechanism does not enforce us to, if we are end-to-end following the reactive streams or Akka streams thing. If we are in the Akka paradigm end-to-end. Yes. So that's about the buffers or the back pressure. Let's take a small detour and come back to a bigger example of buffering or back pressure. So we as a developer, right, as I was talking some developer things, so let's say that's where we come in. So we understood source, sync, and all those things which Shivani explained initially, right? But in our day-to-day development, we don't want to bother about what is a source, what is a sync, and the flows, right? We want a simple programming model, and that's where Akka comes a lot of handy. It provides these functional collection APIs, as some of us might know them as, right? We have map, filter, reduce, stream, fold, drop while. We know these APIs. If we are using Scala already, we have used them in collections, or if we are using Java streams or JavaScript, also JavaScript list and other things provide this similar APIs. Also Kotlin's collections also, I think, provide APIs onto the similar lines. So we as a developers know these APIs, we know how to use them and what to expect when we are using them. And that's how our regular coding of the Akka Streams is concerned to. That's what we are deal with on day-to-day basis. So it just simplifies our day-to-day work while we are imagining pipelines in our head, the data pipelines in our head. So that was a small detour. Okay, going back to the slides. So we understood, right? Back pressure is just a flow control, and a flow control which is controlled by the sink or the consumer of the data, and not the source of the data. Source needs to just wait till there is some demand, and here consumer is the king who decides whatever needs to, how many elements to ask and how to process the data, at what speed to process the data at, and slowing down the producer to match the consumer speed. That's what we ultimately wants to do when we are into reactive streams or Akka stream, when we are using the Akka streams. So that's about the back pressure. Whatever examples we have seen till now are in the same process, right? Though there are some asynchronous things which we saw, the execution is asynchronous, but it's in the same process. And to understand how can we scale this up, we have a very small crude example here, which scales across multiple processes and which can help us understand how back pressure scales across multiple processes when we have data flowing from one system to another system or one process to other process. Just give me a second. Some noise. Yeah. Right. So we have a simple example here. We have a stream of numbers, a service which gives back stream of numbers on requested, and then we have a, that's what I call it, streamer, some funny names, and then we have a doubler which will take that stream of numbers, double it, and then give it to whoever is asking for, and then we have a client who will just request the doubler the numbers. And we'll see how the back pressure plays across this example when we start it. Here we are using some help from a module called Akka HTTP, which is a HTTP library, not a framework, built on top of the Akka Streams. So it provides all the things which we talked about the streams. Over on top, it provides some HTTP support. So I'll just use this for the HTTP, and I'll also explain how HTTP is helping us here. So let me just get the setup up and running, and then we can talk about some other things than Akka and Akka HTTP, or Akka Streams for that matter. Okay, and the last one here. Okay, whenever it starts. So we can start. We know TCP protocol, right? TCP protocol guarantees we day in day out we use. Everyone uses it here. Everything goes via TCP only. But TCP as a protocol, we know property of it is, right? It guarantees that no data will be lost when we are doing the transmission of the data. And what happens? And we also know that there are buffers on the both side of the socket. So if you have a socket, a TCP socket, it has a receive queue and a send queue. I'll also do this one and explain you later on what that happens. Okay, but some data has started flowing, as you can see, right? Both the two processes, and I had requested some data from here. Both of them have started and producing data. Yeah, let's come to the example later on. So queues, as we were talking. But one thing TCP does while transferring the data around is the send sockets always know how much buffer space is left on the other side, and it needs to know those things because again, I'm sorry, it's work from home things. So sorry. So the send queue knows the size of the buffer, whatever is left on the receive side, and that's how we make sure that no data is being lost, but we are just transmitting data in a non-lossy fashion, and that's how the TCP works. Here we are taking advantage of that thing just for the demonstration purpose, because it's same. If the receives, it's same in with the reactive streams. Because if the receive socket is not able to take receive buffer is not able to take any elements, it will let the send queue will know that it's not able to take any more elements, and it will stop pushing the data. And that's how kind of back pressure also works in the TCP. That TCP is also a mechanism which puts back pressure onto the processes if there is no data consumed from the downstream. And that's what property plays very well with Akka Streams and TCP. Those both of them share the same property, and it helps us in the day-to-day data processing. So what has happened in our example? Let's coming back here. Yeah, so coming back here, I had made a curl request from here, right? So we have a streamer running here, which is creating the number stream, a doubler which is doubling the stream, and we have a client which requests on 1990, and this is where the doubler is running. So we start getting data, the double numbers as we saw, right? We get the data, and eventually what I have done is a control Z, which suspends the curl, not terminates the request, right? It's not terminating, it's just suspending and saying I will not take any more data until I'm foregrounded or someone wakes me up. And that's what the curl is state into. But what did that do? Eventually, the doubler gets to know that the curl is not able to take the data, and the doubler stopped by its own because it's not able to push any data downstream. And the same thing, the streamer knows that the doubler is not able to take any data anymore. Let's stop pushing the data. And where can we see that? Here. So here we see, right? This is the receive buffer of the connection which is made between this random port to 1990. And we know 1990 is this. We can guess that random port is this one of curls. And we see the buffer is full. There is slightly any movement in the buffers. And same thing happens when we have here we have the 1990 port to connect into some random port where the connection is made from this port to here for the streamer. And that's how all the data here is clogged up like a water pipeline where we have closed the tap, right? Or there's water throughout the pipeline, but the tap is closed and no water is flowing now. And how do we make the water flow? So if I do it here now, if I foreground the curl, we see, right, again this process started producing the data, and right after that the streamer also started producing the data. And that's how the backpressure plays when we are across multiple processes with some help of TCP. That's how we can do the backpressure and make sure our data transformation or the data producers are following the speed of the whoever is consuming the data downstreams. Okay, I hope this helped you visualize how the backpressure plays across multiple processes. I think we have slightly overshoot the timing, but I hope people are interested and can stay for a few more minutes till we finish the thing. Okay. So again, the example explained, right? As we saw, we have a similar the data and the demand channel flowing in. Demand channel and more elaborate view including the sockets here, as we were saying, into the watch terminal. So we have streamer which is writing to a socket, some reading socket, and that's how the three processes are talking to each other. Okay, coming on to so this is all about the project Akka Streams, and we can talk about the project Alpaca next. I think this is something as a developer, something very useful to us because as we are talking about Kafka and RabbitMQ, right? Okay, so what is Project Alpaca? So it's an open source initiative which Akka Streams kind of take care of. Here, there are many stream-aware implementations of the clients written for the data sources which we use on day-to-day basis. For example, Cassandra, we have heard these names, a Kafka, as we heard the mention, right? Some Parquet things or Amazon S3, and the list goes on here. All the clients which are provided for all the systems from where you can read the data from and write the data to. And the magic real here is everything here is implemented with Akka Streams. And if you choose Akka Streams to talk to any of these sources, you get all the clients out of the box, which are community maintained and open source. So this is where I think the Akka Streams very flourishes, and this is where the real help of the Akka Stream we get, other than the developer help of the DSL and everything we talked, right? So if you're using any of the technologies which are listed here, and or you are about to work with them, I think Akka Stream is something you can look forward to or try to give it a try, just to see how can you complete your use cases. So that's about the project Alpaca. I won't go to detail of everything here. There are a big list, and that's all I think we have for the today's presentation. So these are our references, I think, references and some YouTube videos which helped us prep. And thank you. It's me and Shivani Thorat. Yep, I'll stop sharing, and I think we are open for questions if people are interested. Yeah, whatever questions we have.
I have a question.
Yep.
I mean, while processing or while creating the materialized view, I mean, does the Akka framework by default supports batching concept or sliding window concept, so that I can process my like elements from the source, I can batch it, and then I can sync those processed
Yeah,
elements.
it does.
Oh, it does. Okay.
Yeah. So all the data processing, you can do it in batches or, as you said, sliding window. It's possible.
It's already there in the framework, but just by configuration we can use it. Okay.
Not by configuration, by coding, right? There are DSLs provided for batching and doing the thing. So
okay,
you can use APIs which are provided there.
Okay.
Yeah. Okay. Yeah, there is a link for the feedback in the chat box. Please drop your feedback. I think we really look forward to the feedback as we are learning new here also. We are also learning. So yeah. Any more questions? I think.
No, I think it was very interesting topic and well delivered. Like I liked it very much.
Thank you.
Thank you, Vinesh.
Thank you very much.
Thank you, Shivani and Shubham, for presenting. Yeah, Shubham, please go ahead.
Oh, I was asking if there are any unanswered question in the chat box, but maybe no, we answered them all.
Yeah,
Great.
we have covered all. So while people please open the idea board link that I have shared and let us know your feedback and also the topic that you want us to cover in future. And also we can use this time for more questions.
Yeah, did you overshoot the 7 minutes? But yeah, interested people can stay back. That's all. Yes, thank you, people. Thank you for joining.
Thank you all. Thank you for joining.
Thank you.
Thank you, everyone. See you next time as well. Bye.
Sure, bye.